Greetings. Okay, for this problem, we're trying to find all relative extrema for f of x, which is this expression here. So the first thing we want to do whenever we're trying to determine relative extrema is we want to make sure we understand the domain of the function because we want to know exactly where we're looking for these relative extrema. It's not the case that every function we're going to be dealing with has a domain of all real numbers, and so and this one doesn't. And so we have to make sure we're looking in the proper place for these relative extrema. So remember, for domain considerations, we've got to figure out where there may be any division by zero occurring and throw those values out. And although that's not happening in this case, we would look for even roots of negative numbers and throw those cases out too if that were happening in a particular function. But in this function here, all we're dealing with is division by zero. So notice we have x squared in the denominator of the first expression, first term in the expression, and therefore x cannot equal 0. But no other numbers give us any issue. No other numbers give us division by 0 or even roots of negative numbers. So our domain is going to be, and I'll put it in interval notation, negative infinity to 0, not including 0, so we use a parenthesis, and then union with 0 to infinity. Again, a parenthesis on 0 because we're not including it. We also don't include the infinities because they're not numbers, so we leave those as open or parentheses. It's an open interval, so leave parentheses on the end as well. So it's on this domain that we're going to be trying to find the relative extrema. Now to find relative extrema, the first thing we need to do is look for critical numbers or critical values. To define critical values, we need to figure out where the derivative is either equal to 0 or where the derivative is undefined. And so let's find the derivative so we can start looking. Now it may be helpful to rewrite the function with the x squared term in the numerator so that you can just straightforwardly apply the power rule and of course the constant multiple rule in taking this derivative. It's not necessary. Some people can see the pattern quickly enough without doing that, but it might be helpful this way. So this becomes negative 250 x to the negative 3 minus 2 as our derivative. Now, some students lose focus with the negative exponent, and they forget that the negative exponent means that that term is in the denominator. So let's rewrite this really quickly to make sure that we don't lose sight of that. So this is negative 250 over x cubed minus 2. And it would probably be helpful to get this as a single fraction so that we can more easily define or find where the critical numbers are. So as a single fraction with a common denominator of x cubed, we would get the negative 250, which already had a denominator of x cubed. And since it was just minus 2, we need to multiply the 2 by x cubed in order to get the common denominator and whatnot. So this is our derivative as a fraction, or rational expression if you want to be more technical about it. Now from here, there are two things we need to look for, and we've already talked about that. We need to figure out where f prime is equal to 0, and f prime, or a rational function, equals 0 when the numerator is equal to 0. So I can just take that numerator and set it equal to 0. I do have to be aware, well, I gotta squeeze this in here. I do have to be aware that I want to make sure the denominator is not 0 at the same time, or else otherwise the function is undefined. So there are two parts to that. I need to know when a fraction is equal to 0, when the numerator is 0, and the denominator is not. So I got to make sure I just at least mentally check that part. So if I move the negative 250 to the other side and then divide by the negative 2, and we get negative 125 equal to x cubed. Some students forget that you can take a cube root of a negative number. You can take an odd root of any number, positive or negative or 0, and the result just keeps the same sign. So this actually works out to be negative 5. And obviously the denominator is not going to be negative 5 at the same time. So this is one of our critical numbers. The other thing we need to do is determine when the function is undefined. So f prime is undefined when, or a rational expression is undefined when the denominator is equal to 0. So that's when x cubed will be equal to 0, and that's when x equals 0. However, X equals 0 is not a critical number because for a value of x to be a critical number of a function, the value needs to be in the domain of the function. And as we said way back at the beginning, 0 is not in the domain of this function. So 0 is technically not a critical number for f, but it is still, something we need to be aware of that causes the derivative to be equal to 0. Now from here, what we're going to do is we're going to take those values and we're going to divide the domain of the function into subintervals on which we're going to test values of the derivative to see if the derivative changes sign from positive to negative or negative to positive around those values. So negative infinity to the smaller value, negative 5. I shouldn't say the smaller value because there's only one critical number, but nonetheless. Negative 5 to 0, and then 0 to infinity. We want to make sure all of these intervals are open. We know the derivative is either 0 or undefined at each of these endpoints, so they're not included in our testing, in our values in which we can test. And so we won't choose the endpoints ever in testing in the derivative. So now I need to test f value in this interval in f prime, so you can just choose like negative 6 or negative 10 or something like that. I'm actually going to choose negative 10. That wouldn't probably be easy to calculate with. On this interval here, negative 1 is in this interval, so I'll choose that, and positive 1 is in this last interval, and I'll choose that. So now we have to go back and plug these values into the derivative and see whether or not the result is positive or negative. Now technically we don't even need to know the actual result, whether the actual numerical value. We just need to know whether the numerical value is a positive or negative number. And so when I plug in negative 10 back in the derivative up here, I'm not going to actually do a formal calculation. I'm just going to try to determine whether we get positives or negatives in the numerator and denominator. In other words, if I go ahead and I cube the negative 10 right over here, I get negative 1,000, 10 cubed. I know I'm doing some calculation, but I don't need to. I'm not going to do it all the way. Multiply that by 2, I'm going to get negative 2,000. And then subtracting that makes, adding the opposite. So adding 2,000 to negative 250 gives me a positive numerator. That's really what's all that matters, is I got a positive numerator. And then an abrupt pause in the video. I apologize. So see if I can pick up my train of thought here. So again, when I do the calculation of plugging negative 10 into the numerator, I get a positive number. When I plug negative 10 into the denominator, I get a negative number, and a positive divided by negative, of course, is negative. So I know on that interval here, we're going to get a value less than 0. I should probably stay to the same color. Less than 0. Now if I plug in negative 1 into the expression here, I'm going to end up with a negative number in the numerator and a negative number in the denominator, and a negative divided by negative is positive, so this is going to be greater than 0. And then when I plug in positive 1, I'm going to get a negative number in the numerator and a positive number in the denominator, and negative divided by positive is negative. So now we are going to be thinking, we're thinking in terms of the first derivative test for relative extrema, which tells us that we'll have a relative extrema at an x value if the derivative changes sign, changes either from positive to negative or negative to positive. Now, at the first critical number that we had, or the only critical number that we have at negative 5, I keep referring to it as if there's multiple, but there aren't. So we see that the derivative is negative before negative 5 and positive after negative 5, which means the function f has to be decreasing before negative 5 and then increasing after negative 5. And so we have a relative minimum happening at x equals negative 5. So at f of negative 5, notice I'm saying f of negative 5. It's the output that is the min or the max, not the x-coordinate. The x-coordinate is the location of it. The output is the min or the max. Okay, I didn't do this calculation ahead of time. I probably should have. So I'm going to let you, dear listener, do that calculation. Find the y coordinate there. Plug in negative 5 into the original function f and figure out what the y value is. But f of negative 5 is a relative minimum. I'm going to abbreviate here a little bit. of f, because f prime changes, that's a little sloppy, sorry, but I'm trying to squeeze stuff in here, changes from, whoops, negative to positive at x equals -5. Now, what about what's happening at 0? Well, we have to remember that at 0, f was undefined. There is no output for f at 0. In fact, we have a vertical asymptote in the graph of f at x equals 0. So although we can see that we have a transition in f prime from positive to negative, you may be tempted to say that that there is a relative maximum value occurring there. Don't. Okay, there is no relative maximum for f on its domain, because f prime does not change from positive to negative at any value within the domain of the function. So it does change from positive to negative at 0, but 0 is not in the domain of the function, so there cannot be a relative maximum occurring at x equals 0. So the only relative extrema that we have for this function is f of -5, whatever value that is, and that would be the answer to the question. Although in my solution, if I was turning this in formally for someone else to read, I would explain that there is no relative maximum and why, so that the reader of my work understood that I didn't just neglect that part of the problem, but I actually did consider whether or not there was a relative maximum occurring at some value within the domain. All right, go study.